Okay. Hello. So welcome to the problem solving space session of spread spectrum communication and jamming. So today is week one of spread spectrum communication technology. We will study direct sequence spread spectrum. We will study the core concepts related to direct sequence spread spectrum and also the uh, philosophy behind spread spectrum. So spread spectrum is basically an communication technique that is used to spread the information among the entire spectrum. So, as the name suggests, though there in a large spectrum, we will scatter a small information in a large spectrum in order to protect the information from unauthorized users or eavesdroppers. So, spread spectrum has been, as has been most communication technologies, spread spectrum has been a brainchild of the World War. So during World War, the Allies and Axis powers they wanted to create some codes which were unbreakable by their enemies, and of course they relied on cryptography for that. But spread spectrum was also a valid method which was patented by the US Army. But the thing is, they did not take that seriously during World War. During the 1980s, the spread spectrum communication technology came alive and it became increasingly popular for applications that involve radio links in hostile environments. So, typical application for the resulting short-range data receivers transceivers include satellite positioning system, 3G mobile communication, WLAN, and Bluetooth. Spread spectrum techniques also aid in the endless race between communication needs and radio frequency availability. That is, spread spectrum, because spread spectrum has the property that only the authorized user can listen. So you can transmit to multiple users without one user interfering into other users communication channel. So one user, if one user has a particular message, another user's message can also be added with that, and they can be decoded separately. The only the message only the intended user will receive the actual contents of the message. For the other person it will be like a noise. So it it is allowing multiple users to transmit in the same radio, and this technology is called code division multiplier access. So spread spectrum technology is one of the key enablers of code division multiple access. Now code division multiple access, as you know, is used in was used in 3G communications, and even today the in military in military technology, spread spectrum is used because spectrum is reliable and reliable. So the justification for spread spectrum is apparent in the Shannon and Hartley channel capacity theorem. So in this theorem, the C is the C is the channel capacity. So C is equal to B bandwidth into log 1 plus signal by noise. So this is the Shannon's capacity formula. Now there is a justification of spread spectrum communication in this. How? Because in this equation C is the channel capacity, which is the maximum data rate for a theoretical BER. B is the required channel bandwidth and S by N is the signal to noise power ratio. To be more explicit, one assumes that C, which represents the amount of information allowed by the communication channel, represents the information allowed by the also bandwidth is the price to be paid because frequency is a limit. So, huh, this B is the required channel bandwidth and S by N is the signal to noise. So if there is a difficult environment where there is a low S by N, even then we can have high channel capacity by using high bandwidth. So even at low SNR, channel's capacity theorem tells if we use high enough bandwidth, we can have a high capacity channel. Now, and so one can maintain or even increase communication performance by allowing or injecting more bandwidth even when signal power is below the noise floor. Okay, so even if the signal power is below the noise floor, that is SNR is less than 1, even then if we increase the bandwidth, our channel capacity can be increased. Okay, so different space spectrum techniques are available, but all of them have one idea in common, which is the key or the code or sequence. That is the key or the code or sequence, however you say, is something unique to the transmitter and its intended receiver. Only two entities know this particular, yeah, this particular symbol. Now to apply an SS technique, simply inject the corresponding SS code. So the spread spectrum code will be injected somewhere in the transmitting chain before the antenna. The effect is to diffuse the information in a large bandwidth. Hmm. What happens is we will use a spreading code which will spread our signal into a large bandwidth and then we will transmit that. This is called the spreading operation, and the effect is to diffuse the information in a larger bandwidth. Now you can also remove the SS code, space spectrum code, using a despreading operation, which before the data retrieval. The effect of despreading information will be to reconstitute the information in its original bandwidth. Obviously, the same code must be known in advance at both ends of the transmission channel. Okay, so to have a perfect spreading and despreading, the same code has to be used in both direction, both transmitter and receiver. Okay, so yeah, so this is the spread spectrum. So spread spectrum codes are injected in the transmission chain with and mixed with the data before it being transmitted. And similarly, spread spectrum code is mixed with the receiver chain to the despread the data. So the main concept here is that they both have to be the same pre-agreed sequence, or else this won't work. So the same pre-agreed, these two have to follow the same pre-agreed sequence. Then spread spectrum. Now the spread spectrum has some effects on bandwidth, power, etc. So what happens with the respect to the bandwidth is it is spread in the bandwidth. So if it is spread in the bandwidth, because the total signal power is constant, it is not adding any power. It is just spreading the bandwidth. It is not adding any power. So what happens is it becomes flattened. Huh. It becomes flattened, and because the data becomes flattened, the power becomes flattened. It is relatively of low power. The spectral density is low. Now so the effect of the spectral is effect of the spreading operation is that bandwidth increases and spectral density decreases. Similarly, despreading can be done. Now similarly, despreading will of course reduce the bandwidth and increase the energy. Now the one thing that is natural to ask here is that the bandwidth is a very limited resource. So why should we use so much of bandwidth to transmit a symbol that can be reliably transmitted in a much lower bandwidth? So we are using the same number of bandwidth, same amount of bandwidth to transmit a much lower amount of data. So because we are using the more number of bandwidth, more bandwidth, then we cannot justify that because bandwidth is a limited resource. But there is one compensation which can be offered as a justification, and that compensation is that we can use multiple users. So even if all of them are occupying a large frequency, there are multiple users. Previously, you could transmit one user's data in a single frequency, but now you can transmit multiple users data in the same frequency band. So that offsets. So if your say n times your n times more bandwidth is required for transmitting spectrum signals, this n times more bandwidth can be compensated by the fact that you can now serve n users. But of course, if there are not that many user requirement, then of course it is harder to justify spectrum. But this is one compensation. Now, spectrum, of course, is a wideband technology. So, as opposed to regular narrowband technology, the spectrum process of spreading is a wideband technology. And okay, so this another characteristic of spectrum is its resistance to interference and anti-jamming effects. The characteristic interference in jamming signals are rejected because they do not contain the spread spectrum signal. So even if there are different kinds of signals that are coming in the environment, they are interfering with our signal. Even then, the effect of them is muted. Why? Because there is a unique code, like we have said, there is a unique code. That code only can decode the spread spectrum signal. Nothing else can decode the spread spectrum signal. So when something of an interference comes, of course it cannot be decoded with that code. So it is rejected as noise. Similarly, if there is some other signal, it cannot interfere with our spread spectrum because they do because the key because the key that is there can only decode message of a certain kind, it cannot decode random messages. So only if the message is dot producted, multiplied with the corresponding code, only then we can reliably say that we have decoded. Else, if there is some random signal, we can simply reject that. So you can practically ignore the interference as it does not include the key used in spreading information. Now, another is resistance to interception. That is, the interference is another different thing, interception is different thing. Interception means a eavesdropper is trying to listen to your signal. But every receiver has a noise floor. Noise floor means any signal that is below that floor will be considered as noise. So any signal that is below that floor will be considered as noise. Thus, this any signal we interpret it as noise. So because you are spreading the data, so you are spreading it over a large bandwidth. Because you are spreading it over a large bandwidth, it is being decoded as, because you are spreading it over a large bandwidth, it is being decoded as below noise floor. So it is going below noise floor. So the receiver, that is the eavesdropper, the spread spectrum one, the spread spectrum receiver, the authorized receiver, they know that the signal will come at a low level. So of course their receiver sensitivities will be tuned like that. But but another thing is this. hmm, it has to be it will become invisible. Now another advantage is the resistance to fading. So fading means the reflected path. So as we know, wireless signals can be reflected from various sources, various reflectors like buildings, trees, or atmospheric reflection. So these reflected waves, they arrive at a delay and they interfere with the main signal. This is called fading. But this fading is mitigated because the signal R that is coming, that is rejected in its entirety. Why is it rejected in its entirety in spread spectrum? Because again, spread spectrum has a unique key, and that key can only unlock the signal. Now, so the reflected wave that is coming, we know that spread spectrum will reject that reflected wave. Why it will reject that reflected wave? Because it is a delayed signal, and a delayed signal will immediately, if you multiply it with the code, it will give you erroneous result. So the code and the signal have to be perfectly synchronized for them to combine and give you a perfectly good data. If the signal is delayed, then your signal is useless. It becomes useless because the code will reject that. The code will not give any meaningful data multiplying by the code. Now, Spread spectrum allows CDMA. So note that spread spectrum is not a modulation scheme. It is a like it is a spreading scheme. So it is spreading it across the band, but it is not fundamentally changing the nature of the signals. So, but it can be used to implement one kind of multiple access that is called CDMA. So as you might know, there is FDMA and TDMA. So FDMA means the users, multiple users, transmit their data simultaneously in time, but separated at various separate bands. So they are separated at separate bands. Now time division multiple access means they are transmitting over the same band, but they are transmitted one after another. So they are divided in time. So you divide either in time or in frequency. Now CDMA is fun in that way that it does not use frequency or time separation. All the user data is transmitted simultaneously, and all the user data is transmitted in the same frequency bandwidth. So what does it change? Well, it changes the code of the it changes the shape of the signal. So it is spread, and what happens is the all the users signals together are jumbled up such that only the intended receiver can receive the signal. Now So the next part of this spread spectrum is the generation of the key. At this point, we know that the main spectrum characteristic is the presence of a code or key, which must be known in advance by the transmitter and receiver. In modern communication, the codes are digital sequences that must be as long and random as possible to appear as noise-like as possible. But in any case, they must remain reproducible. So we are not using raw noise because raw noise is not reproducible. It is not controllable. We don't know what we are getting. But here we have to make something that is secure but at the same time reproducible. So we cannot use pure noise. Instead, we use something called pseudo noise. Pseudo noise is ultimately deterministic, but the cost of decoding it is very high, and brute forcing it is nearly impossible. So we have to use a pseudo random code of pretty high length. So this is now the pseudo random numbers are generated using a pseudo random number generator, which is based on a feedback shift register. So here we see a feedback shift register. So here the register is this register and a XOR gate. So the bits are, yeah, so this is the feedback shift register. Next, pseudo random noise sequence is generation is beyond the scope, so we will not go there. But there are multiple famous pseudo random noise sequence like Barker N sequence, Gold, Hadamard, Walsh, etc. Now we will go into the more different modulation spreading techniques. So the different spreading techniques are, first is the direct sequence. In the direct sequence spread spectrum or DS3, in DS3 the data is modified using the pseudo-random noise sequence, whereas in the FHSS or frequency hopping spread spectrum, the frequency of the carrier is modified by the pseudo-random noise sequence. So, and in the time hopping spread spectrum, the timing of the signal or the delay of the signal is controlled by pseudo-random noise sequence. Now, the first technique that is under scrutiny is direct sequence spread spectrum. In this technique, the PRN is applied directly to data entering the carrier modulator. The modulator therefore sees a much larger bit rate, which corresponds to chip rate. So the pseudo-random noise sequence is directly applied to the data. So direct, that is the DS3. There's the modulator, which will come after after we have added the code. We'll see a much higher data rate. Okay, so here we have the in this technique the PRA is applied directly to the data. So we can see that. Let's take an example of how that is in real life, how the data is applied. So here we can see that if you look carefully that there is a two users. Let us assume there are two users that transmit, say they transmit say two symbols d1 and d2. A symbol is a bit obtained after encoding and decoding of noise and data. Now user 1 transmits symbol d1 and user 2 transmits symbol d2. So and the two users are assigned distinct codes 1111 and 11 minus 1 minus 1. So to transmit the to transmit symbol with code, the symbol is here the symbols d1 and d2 have to be transmitted by user 1 and user 2. User 1 has the code 1111 and user 2 has the code 11 minus 1 minus 1. Now to transmit the code, the symbol is multiplied with the code. So user 1 has the code 1111 and it has the symbol d1. So the spread spectrum information for user 1 is d1 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 d1. Whereas for user 2 it is d2 into 1 1 minus 1 minus 1. So it is d2 d2 minus d2 minus d2. Now these are added together. So the resultant signal is the addition of user 1 spread spectrum signal and user 2 spread spectrum signal. So it is d1 plus d2, d1 plus d2, d1 minus d2, d1 minus d2. So at the receiving end, to recover the symbol of the user, it is multiplied with the code and correspondingly we add. Now to receive them, we multiply again with the code. So user one's intended receiver will have the code 1111. So he will simply use 1111 as and multiply it to get d1 plus d1 plus d1 plus d1. So it is 4d1. So he effectively retrieves d1. So user 1 retrieves d1, which is its intended message. And for user 2, it has to you can multiply with 1 1 minus 1 minus 1 and you will see it is d2 plus d2 plus d2 plus d2. So it is 4d2. So we can say that d1 and d2 have been effectively So the only way this is possible is if these codes, the user codes, are orthogonal. Because if you multiply 1 1 minus 1 minus 1, then you get d2. But if you multiply something like minus 1 minus 1 minus 1 minus 1, something like that, then, or minus 1 minus 1 1 minus 1, something like that, so some other code. So if you try multiplying this with some other code, you will see you will not retrieve d1 exactly, you will retrieve d1 plus something, d1 plus something, d2, which is not the intended message. So the effectively point is that only these two symbols, 1 1 1 1 and 1 1 minus 1 minus 1, can decode into d1 and d2. No other code can. So the receiver has to have the exact code. So this is DS3. So this is the core technology behind CDNA. Now, how many times does the bandwidth spread? Because the message length is the same as the sequence length. So I say code length. So the code sequence length is whatever the code sequence length is, the amount of data that needs to be transmitted. So we have to have bandwidth corresponding to that. Hmm. So civil application uses spreading factor between 10 and 100. Military application use up to 10,000. So spreading factor 10 to 100 means you use, so you use code length that is 10 times the symbol. So if you have to have 3 bits, you have to transmit 3 bits, you have to use 30 chips, 30 sequence chips. Now, so if there are n possible orthogonal codes, the n users can access the medium simultaneously. That is clear. So with that we summarize DS3 as bandwidth is spread with the help of code called spreading code. The code is independent of the data, and by using unique code, all users transmit using entire bandwidth. So by using this unique code, all users are transmitting data the using the entire bandwidth, and the receiver receives the sum of all those signals, and it synchronizes with the code of the sender. To recover the data, the receiver correlates the received signal with the user code. So now that DS3 is clear, we will go into some problems for DS3. The first problem is that consider a DS BPSK spread spectrum transmitter. Let DT be a binary sequence 1101 arriving at a rate of 100 bits per second, where leftmost bit is the earliest bit. So 1, then 1, then 0, then 1, and it is arriving at a rate of 100 bits per second. Now let CT be the pseudo-random binary sequence, which is given as 1001, 1011, 1100. sorry, 1000. So with a clock rate of 300 hertz. Assuming a bipolar signaling scheme with a binary 0 and binary 1 represented by signal levels -1 and +1, the final transmitted binary sequence corresponding to the bipolar signal sequence is. So that is your question. So take 5 minutes and find the dot product of this, convert it to bipolar, convert it to bipolar, convert this to bipolar, and do a dot product, and take 5 minutes. Okay, so we will look into the first question. So here first we have to convert 1101, and 1101 is plus 1 minus 1 plus 1. So we will convert that as plus 1 is 1101 is plus 1 minus 1 plus 1. So it is converted. Now we have the code. The code is 1001, 1011, 1000. So 1001 is plus 1 minus 1 plus 1. Then further we do the accordingly. Now the main part here is the spread spectrum. So the spread sequence is obtained by spreading xt. So you have to spread xt. You have to spread xt such that the, because we have to take a dot product, right? And dot product can only happen if the two sequences have matching length. So if you take these two sequences, then you have to spread. This is 4 length sequence and this is 12 length sequence. So how many times do we have to repeat? We have to repeat 3 times. So each chip in the sequence, each symbol in the sequence is repeated 3 times. So plus 1 plus 1 plus 1, then again for the next plus 1 plus 1 plus 1 plus 1, then for the minus 1 minus 1 minus 1 minus 1, then again for the plus 1 plus 1 plus 1 plus 1. So that is the new spread rate information. But we have to multiply that with the code to. So we take the spread rate sequence and we take a dot product with the sequence with the code. So we take a dot product with the code and what we get is the PT. The PT is the exact binary sequence that is spreaded. So if you take the binary conversion, bipolar to binary conversion, it will become 1001 10000000. Next, what is the question? The question is, what is the next question is what is the next question? What is the bandwidth of the transmitted spread signal? Now, the bandwidth, if you want to try, I will give you 2 minutes. Think about what is will be the bandwidth. Then we can get back. So the bandwidth of the transmitted signal will simply be the bandwidth of the sequence that is being transmitted. The bandwidth of the signal. Oh, 1 minute. So the bandwidth of the transmitted signal will simply be 300 hertz because we have matched the signal with the signal length with the pseudo noise length, and the pseudo noise was being transmitted at 300 hertz. So now obviously because we have the same number of bits, the data spread sequence will be transmitted at the same speed. So it will be transmitted at 300 hertz only. Next, the processing gain. So what is the processing gain? So that is one definition that we need to know. What is the processing gain? A processing gain is a very general term, but here processing gain means the chip rate by the data rate is chip rate by data rate. Now chip, as we know, is if your code is plus 1 minus 1 plus 1, so plus 1 plus 1 minus 1 and plus 1 are individual chips, and they together make data. Now together make one symbol. So chip rate and data rate, here chip rate is 300, so 300 samples are being transmitted. But what is the data rate? 100 kbps, sorry, 100 bps. So 300 by 100, so the processing gain is 3. So if you take it in dB, it is 10 log 3, that is 4.77. So the correct answer is 4.77. Now we have a interesting problem that there is a estimated delay at a spread spectrum receiver. It is delay is equal to one chip time. So what is a chip time? So 300 hertz means 300 chips are transmitted at 1 second in 1 second. So chip time simply means 1 by 300th of a second. So so it is the estimated delay So the one chip time 1 by 300. So the despreaded sequence, despreaded and decoded signal sequence will be. So we have a delay, and delay is one chip time. So the chip will get all the code here will get shifted by 1 bit. So the one here will come at 0, the next 0 will come at here. So 1 will come here, then 0 will go here, like this. So it is getting shifted. So of course shift 1 and then you have a new code and repeat the same process. So basically multiply the spreaded sequence that we have got here, and we will get the spreaded sequence with the modified code, and we will get the final sequence. So work it out, final sequence, and find out, then convert those bipolar into bits and tell me what is the answer. I will give you another 5 minutes for that. After that, we can come back to the answer. Okay, so now we go to the solution for this one. So the solution is 0001 if you have got it correctly. So what happens is, because we have delayed the GT, so what happens is the correct GT was something like this: plus 1, minus 1, minus 1, plus 1, and so on. Now, because of the delay, this plus 1, this plus 1, this particular plus 1 has come here, one chip delay. So this plus 1 has come here. Next, the two minus 1s have shifted 1 place each. So they become minus 1, minus 1. Then plus 1, then plus 1, then minus 1, like that. Finally, in the vacant space left in the first spot, of course, because PN sequence is a feedback shift register, cyclical process. So we will get back the minus 1, that is here. this will be rerouted here. So we will get something like this. So we have the delayed sequence, and our spread sequence is, of course, this is the transmitter. So this is what is sitting at the transmitter. So this is already done, but the delayed GT is sitting at the receiver. There is no delay in the transmitter, of course. So when you multiply the already spreaded sequence, that is PT, with this sequence, you get, multiply them, and then you take 3 bits at a time. Why? Because originally we took 3 chips to mean 1 bit. We spreaded 1 bit into 3 chips. So now we will combine 3 chips to get 1 bit. So 3 at a time, and we will get, this is 0, this is 0, this is 0, this is 1. Majority logic decoding means this is -1, this is -1, this is -1, this is +1. So it is 0, 0, 0, 1. So the final, because of 1 by 300th seconds of a delay, 1 by 300th seconds of a delay, you are getting a bit error rate of 50%. You wanted to transmit 1101. Instead, you are stuck with 0001. So how many errors are there? 2 errors are there. So that was the next question. So we have solved the next question too. So the number of bit error in estimation delay is 2. So because we wanted to transmit 1101, we ended up transmitting 0001. So there are 2. Now there were total 4 bits, and we committed error in 2 of them. So it is a 50% bit error, which is as bad as it can be. So because of 1 by 300th of a second, we ended up with a 50% bit rate. So synchronization is of the utmost importance in DS3. That is why DS3 has been favored by other sequences which are not as sensitive to synchronization requirements as DS3. Now, a DS3 system transmits at a rate of 1 kbps in the presence of a tone jammer. The average jammer power is 20 dB greater than the average desired signal power, and the required bit energy by jamming power spectral density to then the average jammer power is 20 and required to is 10 dB. Okay, so let's look at the question first actually. Yeah. A DS3 system transmits at a rate of 1000 bits per second in the presence of a tone jammer. The average jammer power is 20 dB greater than the average desired signal power, and the required EB by J naught to achieve satisfactory performance is 10 dB. So the ratio of spreading bandwidth Ws to the transmission rate is, okay, so the average jammer power is 20 dB greater than average desired signal power, and required EB by J naught to achieve satisfactory power is 10 dB. So what is the ratio of spreading bandwidth and transmission rate? Okay, so I will leave you to it for 5 minutes, then we can take on the problem. So if you want to directly check the solution, please fast forward this video by 5 minutes. Thank you. Uh, So the ratio of spreading bandwidth to transmission rate is okay. So the first is we have to interpret the system. So the system is EV by J naught is the spreading energy and jamming PSD. So bit energy and jamming PSD. So the ratio of spreading bandwidth to transmission rate is, so the EV by J naught is basically EV. What is EV? EV is the average power by the bit duration into the bit duration, and the jamming power spectral density is the average jamming power and the and the spreading bandwidth, the bandwidth over which the jamming is done. So PSD is basically power by frequency and energy is power into time. So we rearrange the terms. So PAV by JAV into WS by R. So PAV is the average power, transmit power, JAV is the average jamming power, TB equal to 1 by R denotes the bit duration with R being the transmission rate. So now we have to, what do we have to find? We have to find WS by R. So WS by R is EV by J naught into JAV by PAV, or EV by J naught plus JAV by PAV. So the average jamming power is 20 dB greater than the average signal power. So JAV by PAV is 20 and EV by J naught is 10. So total it is 30 dB. So the ratio is 30 dB. So the correct answer is option 4. Next, the bandwidth of the spreaded signal is, so the R is 1000 bits per second. So it is simple. WS by R is 30 dB. 30 dB means 10 to the power 3. It is 30 dB, which is 10 to the power 3. So WS is 1000 times the transmit rate, which is 1000. So it is 10 to the power 6 hertz or 1 megahertz. So correct answer is option 1. Let's see. And voila, the correct answer is option 1. Now, next question. A ground to synchronous satellite link is to operate a data rate 10 kbps. So, a ground to synchronized satellite link is set to operate at 10 kbps data rate with a ground station antenna at 80 feet and a transmit power of 10 kilowatt. It employs a 10 Mbps direct spread sequence DS3 spectrum code. The receiver EV by Gen 0 required for reliable communication is 20 dB. A jammer with 10 feet antenna intends to 100 feet antenna intends to disrupt the communication link. Assume equal space and propagation loss and that receiver noise is negligible. So lots of things are there. So the first question is the processing gain of the spread spectrum system. So this is pretty easy. This does not have anything with to do with power. So it is chip rate by data rate. So the data rate is 10 kbps. So we just have to find the chip rate. So the chip rate will be 10 Mbps because it employs a 10 Mbps direct sequence spread spectrum code. So here you can directly get the solution because chip rate is 10 Mbps and data rate is 10 kbps. So processing gain is just the ratio of these two. So it is just 1000 or in decibel 30. So 30 dB. Now the jammer power required to disrupt the communication system. Now a power so the jammer power required to disrupt the communication system is given by EV by J0 into jammer power by gain and the aperture areas. So EV by J0 is given to be 20 dB, that is the jamming margin. The jamming margin is 20 dB and the power of the jammer is then basically the transmit power by jammer margin into the processing gain GP, which is 10 to the 3, into the aperture areas, which is 80 and 100 feet. So 80 square by 100 square. So if you simplify, you will get 64 kilowatts. So 64 kilowatt power is required to jam the signal. So that will be all for today from my side. See you in the next week. Thank you.